So, welcome everyone. Welcome to GPUs and CPUs, a rapid-fire set of performance optimizations. I gave this presentation a couple of months ago at GDevCon in Brighton. I added a little bit on top of it. It was mainly focused on CPUs, but lately we've added a couple of functionalities to the G2CPU toolkit, which will nicely complement what we're doing here. So, for those of you who don't know me, I'm Natan. I'm the CEO of G2CPU, the high-performance GPU toolkit for LabVIEW. I'm an architect, I'm an instructor, and I'm a champion, and I'm just a LabVIEW enthusiast, right? We love it, we want to get the most out of it, and then suddenly someone sends you something over LinkedIn that really shatters your trust. Hi Natan, I'm having one question. Why do people use LabVIEW? Instead, they can use Python, right? Which is free and faster than LabVIEW. I did not doctor this. This is truly something someone sent to me. It hurt me. And as you can see, it was at 10 o'clock at night. So I had actually trouble sleeping because I was like, no, but why? Why would Python be faster? It doesn't make any sense.
It's a very subjective thing to say.
Yes, absolutely. And by the way, free. There is a free community edition. So, as a palate cleanser, let's see how far we can push it. So this is a project I'm involved with my toolkit. It contains FPGAs, GPUs, CPUs, and it shows how far we can push LabVIEW. So this is a project between Qblox and IMEC Life Sciences. And what they're doing is single molecule detection, right? DNA, protein, stuff like that. Detecting single molecules, which is something insane to think about. So all the instrumentation is done, the programming is done in LabVIEW. The instrumentation design that we came up with allows for the following characteristics. So they wanted a high channel count, 1 to over 10,000 channels all being acquired at the same time. Now, that being said, this is not with NI hardware being acquired just because the sensing of these molecules, it's really specific, so it's done through custom ASICs. High sample rates per channel between 10 and 50 megasamples per second, which gives us an eye-watering data rate of between 100 megabytes per second to even over 1 terabyte per second worth of data being processed. This is possible in LabVIEW. LabVIEW is such a great language. You can do FPGA, GPU, CPU, all within the same language, and you can really push it to its limits, and even beyond, quite simply. So going back to the previous, Python can't do this. Python's great for AI, but if you want high throughput, stick to LabVIEW. Now, what this customer also wants is inline processing, right? We don't want to send all that data to a disk. Disk manufacturers, they would love to sell you disks, right? A couple of terabytes, petabytes, yottabytes. It becomes really expensive. So what they want is inline processing and with data reduction and just-in-time results to actually, for their operators to see, okay, what does the data look like? Is my test going well? Do I need to stop it? Do I need to restart it? What's the health of my system? And also get just-in-time results. By the time the test stops, the results are already there, instead of post-processing and so on. So the data reduction is great. We're searching for features. When is a molecule coming through? And only that part is being saved instead of this entire data stream, which doesn't contain all that useful information. So that's a little bit of a palate cleanser. So test and measurement, what does the compute landscape look like? Well, for the last couple, I think 8 years, I've been presenting this Venn diagram, which is you have the GPU, the CPU, and the FPGA. They're not competing with each other. They're complementing each other. Each one has a specific set of functions, a specific set of characteristics, which makes it excel in certain aspects. So for example, with the FPGA, it's really great in parallel throughput, processing multiple things at the same time, but also being really low latency. I can get latencies down to single nanoseconds if I want on an FPGA. I wouldn't try to do that on a CPU or a GPU. So low latency, nanosecond to microseconds stimulus response. So from the time you're measuring something to sending back something out, really fast, right? High-speed communication. NI has an amazing suite, and we do use it in the project I just mentioned, of high-speed serial devices, FPGAs, where you can have 100 gigabit Ethernet connections to send data back and forth. Really great stuff. Parallel throughput. FPGAs are great for element-wise simultaneous analysis. Sample comes in, do an action, sample comes in, do an action, and keep on going like that. This is, for example, that project looking at 128 channels, if I do recall correctly, searching for molecules coming in, all being processed at the same time. This is what the FPGA truly excels at. Next up, we have the GPU. That's being so the FPGA is being serviced by LabVIEW FPGA. I don't need to explain to you that that exists. G2CPU, that's my company. We specialize in high throughput, high volume, high everything GPU computing within LabVIEW. It's going to be a shameless plug at the end of this presentation as well. But the GPU is mainly focused on the parallel throughputs and floating points. So batch-wise simultaneous analysis. Now this is different to the FPGA. The FPGA can work with single samples coming in. The GPU likes big batches of data coming in so it can just crunch those numbers in one go. It can process multiple gigasamples per second worth of data. It can do that all day long without any issue. 50 gigabytes per second is not an exception with the latest GPUs nowadays. Floating points, really high accuracy. Try to do that on FPGA. You can do fixed point, but it becomes quite tricky. Floating points, great. And we can do advanced arithmetic. Now, what does that lead to? So I love this little screenshot. Don't worry, I have a zoom function. So what we're doing is we're comparing the GPU versus the CPU, where the CPU is doing 11 megasamples per second. In all honesty, it wasn't the best CPU in single-threaded performance. It was a server CPU. But the GPU was able to manage 6.4 gigasamples per second, which actually gave us a throughput speed up of 560 times. Within the same environment, within LabVIEW, we went from, okay, we can barely keep up to bring it on. Going a little bit deeper, I have a couple of extra here, so 5080, all quite high-end, but not Halo products just yet. Whoops. What's happening here? Okay, we're back. So here we're doing an FFT size, and here we do a throughput of 25 gigabytes per second, doing these really big FFTs for RF analysis, while our I/O speed, getting data to and from the GPU, which is equally important, goes up to almost over 53 gigabytes per second. Same for the PXI system. We all use PXI systems. So downstairs, we are working together with Radix Technologies. There you can actually see this demo, where we have a PXI system and we're constantly streaming from a VST. That's over 5 gigabytes per second worth of data on a single slot. And we can just easily keep up no matter what we're doing. If you're interested, I can talk more about that. It's not the core of this presentation, but it's just as a little frame to what was initially shown. Now, lastly, we have the CPU. And the CPU is equally important as the GPU or the FPGA. It ties everything together. So you have your floating points, LabVIEW controls and indicators, right? Visualization, so your graphs. And it also is fairly low latency. It's communicating directly with all the hardware. It's at the center of everything. So it can communicate the fastest with all these different components. So connecting them, and of course you have large system memory. What does that mean? Well, if we design this well, our CPU side code, we can, for example, stream 7 gigabytes per second to and from a hard disk. And this is just TDMS, by the way. We're going to see this later on, but it's like a little sneak peek. This is perfectly possible in LabVIEW. 7 gigabytes per second of continuous streaming without any issue to a single hard disk. So this presentation, we're going to have a look at data layout. How do data types affect our throughput? Disk I/O, how can we get the most of these latest generations of SSDs? The CPU, how do we leverage the latest architectures from Intel and AMD? these big little architectures and get the most out of it. Algorithms, so what type of algorithms can we leverage for this high throughput? And then of course, lastly, execution modes. How can we leverage all of that together with the GPU to see, okay, how can we get these really high throughput rates? So let's start with the data layout. And I want to do a little bit of a thought exercise on this. So I want you to consider a single sample. It's the atomic function of our job, right? We are test and measurement, we're grabbing data, a single sample. If we represent it as an integer 8 or unsigned integer 8, it becomes 1 byte. So if we consider bytes, this is what the computer uses. The computer doesn't really care for samples. It's a useless metric for it. Bytes is how computers think. 1 gigasample corresponds to 1 gigabyte. Trust me, this becomes really important in just a moment. If we go for an integer 16, 2 bytes, suddenly the amount of data we can represent with that single gigabyte halves. Then we go to integer 32 or single floating points. Again, it halves again. Integer 64, it halves again. Same for double floating points, double. This is the default in LabVIEW when we're doing analysis, right? By default, we grab the double and we do our analysis thinking, oh, it's fine, it just works. Why? Why do we care? We should care. Choosing the right data type has such a big impact on high throughput. Please consider this little program. On the left-hand side, we are generating about 200 million data points, and we're just streaming that into this increment function. I think we can consider that a basic operation, right? What we're doing here is we're also casting it to a specific data type, and we're going to cast it to all the different data types or sizes that are available. And something peculiar starts popping up. If we represent it as an integer 8, we can do about 13.7 gigasamples per second. That's the metric we use. We don't care about gigabytes, we care about samples per second. If we go to integer 16, it halves. If we go to floating point 32, it halves again. If we go to floating point 64, double floating point, it halves again. So the same sample, which might have been captured as an 8-bit or a 12-bit or a 16-bit, is highly affected by the data type we choose. So by just choosing the correct data type, we greatly increase the performance on our CPU. The same with visualization. Now in this case, we have pretty much the same example, except for I hard-coded the type conversion, but I still have a similar table for you. Visualization itself is also affected by the data type. So when we are feeding in these double floating points, and suddenly the UI can't keep up, and we go, oh, what's happening? I need a bit better CPU. I need to optimize my code. Stand still and think. Well, floating point 32, do we really need that accuracy for visualization? Do we really need that to go that far? Maybe we can show it just in i16 and just add a multiplier and an offset to it. So something to consider, that your data type becomes really, really important once your application starts to scale. Now for data storage, I want to try something different. So we have an airplane jet engine, something we would come in contact with or something similar. We have about 100 accelerometers all over the place, 30 kilohertz, 300 kilosamples a second per sensor, so about 30 megasamples a second. We have a 16-bit ADC. Now that becomes important. The test lasts for about 10 hours, and we generate about 1.08 terasamples. These are our metrics. This is what we are interested in, this is what the customer is interested in. Depending on how we represent the data and how we store it, the file sizes, however, become drastically different. And if we store it as it comes in, integer 16, I can store that on this laptop, no problem, and still have plenty of room to spare. If I want to send it over the network or to a USB disk, I can do that quite easily. 60 megabytes per second, it's trivial. I can send that over a standard Ethernet connection you will find in any corporate environment. However, if we go to floating point 32 or 64, the data type we often use, we can suddenly see our file size quadrupled. And if we are sending that to, let's say, a server to store or do post-processing, our data rates have also quadrupled. What does that mean? Well, instead of using the standard Ethernet plug you will find in any corporate environment, we'll have to go to facilities and ask, hey, can we upgrade all of this? And anyone that works in a big company knows how much of a pain that is to try and get that done. It takes ages, way too many meetings for what it should be, and hopefully at the end it actually works. Well, top one, it's not an issue. This brings us to a problem. If we represent this in integer 16, again, the customer doesn't care about that. If we're measuring, for example, voltage, we want to store it as a voltage, not as what the ADC is putting out. How will we do that? Well, TDMS actually has a scaling functionality. So you will find the TDMS create scaling information in the TDMS palette, and it actually provides to the metadata of the TDMS file, hey, this is how I go from your ADC value to the actual represented value. Pressure, voltage, current, and so on. So by just being intelligent about how we store data, we can gain so much in regards to infrastructure and also disk storage. And I don't have to tell you, disks have become awfully expensive the last 2 years. The prices have quadrupled, and data has only increased. So not that great. The same goes for GPUs. Sorry. So for example, if we have a single floating point, depending on the FFT size, whoops, there we go. If we have a single floating point, we can get data between, I think my computer is having a moment, between 20 and 40 gigasamples per second. So that's about, multiplied by 4, so between 80 and 160 gigabytes per second being processed. And that was on this GPU, on this laptop, by the way. If we represent it as double floating points, it becomes worse. Okay, we have 10 gigasamples a second, but we don't even go to 20 gigasamples a second. So sometimes you also need to consider that the hardware itself is not capable of accepting certain data types. A good example of that is GPUs. GPUs are great for floating points, single floating points, integers, but if you provide a double floating point, there's only a very few GPUs that support that. If you then go to double floating point, it will try to emulate it, and suddenly your performance tanks. So keep that in mind. And you will find this in quite some hardware as well, especially in compute accelerators, MPUs, TPUs, and so on. So always keep that in mind. Now, next up, disk I/O. So I already showed it just a moment ago as a little teaser. Disks have become fast. In 2008, we had SATA 2. 2009, we had SATA 3. Initially, they were 100, 250 megabytes per second. They went up to 600 megabytes per second, but that's where they stopped. After that, we had PCIe SSDs, NVMe SSDs. They all started at 2,500, 5,000, or 14.5 gigabytes per second. They have become faster gradually. But as you can see, the amount of data coming through is quite substantial. It matches the data rates of certain captures we're doing. So how can we leverage that? How can we merge those two together? Well, let's bring in TDMS, right? Well, before I do that, I'm first going to explain the testing I've done and what this system is. So this system has a Samsung 990 Pro 4 terabyte. What's in the name? It's PCIe Gen 4 with 4 lanes. It has an advertised read speed of 7.5 gigabytes per second and advertised write speed of 6.9 gigabytes per second. Now, first of all, since when do we trust manufacturers, especially for computer components? It's advertised as theoretical, and no way you should even trust getting close to it. So let's bring in a utility called Crystal Disk Mark. Crystal Disk Mark is a standardized benchmarking utility. Some of you might know it. And it allows you to see, okay, how is my disk going to behave in real life? So we run it, and this is what my system comes up with. 6.8 gigabytes per second reads, and a write speed of 6.7 gigabytes per second. I would dare to say this is what we paid for. This is why we purchased the disk. Why would we want anything else? When we spec a system, this is what we spec. So how would we do that? Well, let's consider a regular TDMS read-writes, right? We open the TDMS reference, we read or write, and once we're done, we close. It's a simplified representation, of course, for this presentation, but this is how we would normally use TDMS. TDMS is great because it's optimized for high-performance streaming. It is highly sequential. This is what SSDs love. So let's have a look at the performance of these functions, right? Ooh, that's not great. A write speed of 2.7 gigabytes per second and a read speed of 2 gigabytes per second. Let's go back to the benchmark. This is what we paid for. This is what we got. Now, I'm a firm believer in pointing something out without a solution is just complaining. So let's go to the solution. So the problem is reading and processing is happening sequentially. So we're reading from the disk and then transforming that data, morphing that data so it's available in the LabVIEW environments. That's cumbersome, that takes time. And this processing scales with the data read-write size. So going to bigger data packages, it only helps so far. You're never going to reach the full performance. So let's have a look at how that looks graphically. So over time, first we do, so when we read, the first thing that happens is there's a disk read action, and then there's a certain processing step in there. Only once that's done, we go to the next iteration, and we read and process. I know it's more complex, it's just for this presentation, so please consider this highly simplified. But it's a good representation of what's happening in the background. So let's go to the solution. We have multi-threaded systems now. This system has almost 30 cores that we can leverage. So why not process on different cores and reads while the other CPU core is processing? What would that look like? Well, while we're processing the first chunk, read the next. So we're reading, processing, all at the same time. Suddenly our disk is constantly busy. And this is the point where I go, well, it's highly complex to implement this, so what you need to do is either DQMH, an actor framework, and start creating all these different actors and make them synchronize. No, NI has done a great job. These functions already exist. If you go, wrong pointer, there we go, into File I/O, TDMS streaming, Advanced TDMS, and we go way down, TDMS Advanced Asynchronous I/O. It's quite deeply buried. But these functions, which ship with LabVIEW, do all this work for us. No need for us to do all this work. It's just pick it up, let's use it. So what does that look like? Let's have a look at the code. This is the equivalent code of what we were doing just a moment ago. We have an advanced open. Please take care, this is not the regular TDMS open, it's an advanced open. We configure our asynchronous reads. How many cores are we using? How big are the chunks? Stuff like that. What's the data type? And then we send it a trigger saying, hey, start. And it will go. And it will keep on going. And in the meantime, whenever something's available, it will become available in the asynchronous read. If nothing's available, it will block. And then once you're done, just an advanced close. There are just 2 extra function blocks, but let's have a look at the performance. That's a lot better. 6.46 gigabytes per second on the write speed and 7.12 gigabytes per second on the read speed. Now let's go back to the benchmark. This is what we paid for. And actually, great job, NI. The read speed even beats the synthetic benchmark. And this read speed, that's done with standard TDMS files. Our data is highly sequential and we can match that. So these TDMS files that I used for this were not artificial, they were actually measurement data that I captured, that I just used for this, just to give a good representation of what you can expect. Really, really, really useful. Now, I had a professor at university, and he says, well, there are certain unwritten laws of nature. And he gave me this magnificent quote, there is the preservation of misery. If you fix one thing, something else will break. So let's see what that looks like. First of all, these new SSDs, they do suffer from temperature, from overheating. So if you are writing or reading for too long and your SSD isn't built for it, it will actually start overheating. Suddenly you will see your performance drop. We also have another phenomenon called cache exhaustion. Now this is something interesting. When we are writing to an SSD, the advertised speed is only for a certain amount of data, and then it falls back to something called the cache exhaustion speed. And that's actually the true speed of our SSD. And in this case, for this system, that was 1.4 gigabytes per second, even though there was advertised to be 6 gigabytes per second. So when we are speccing a system, we shouldn't look at what the manufacturer is telling us. First of all, we need to ask, hey, what's the write cache? How much of that fast memory is there? And once we're done with that, what's the cache exhaustion speed? This is the speed at which your your SSD will run once that cache is full. If you stop writing, it will gradually remove the data from that fast memory into that slow memory, and then you can go back at that fast speed. Yes?
Is this DRAM cache? Is that what this is?
Let's give you a mic. Well, it's also on the video.
Is this the DRAM cache that you see advertised on SSDs? Or is that something else?
It's part of a buffer, but there are also other aspects to it as well. But normally when you look up the data sheet, you will actually see the write cache in the spec sheet. Unless it's really the lower end consumer products, they don't really advertise that because it's often minimal if not existing. So how do we overcome the cache exhaustion? How do we overcome that, well, suddenly our SSDs become slower? Well, the first thing we can do is RAID arrays. Leverage multiple of these SSDs so the cumulative sum of the cache exhaustion speeds is higher than the speed at which we're writing. That's useful. Sorry, I think my computer is overheating. There we go. So
Are you becoming exhausted? Is your cache exhausted?
So the RAID array, it's so we distribute all our writes across all of the SSDs, so we never exceed the cache exhaustion speed, and so we can write for days without the cache exhaustion becoming an issue. Alternatively, there are specialized SSDs which don't have this issue. Their entire SSD is of this hyperfast storage type. Now, why are not all the SSDs this type? Well, cost. They're expensive. So you have to consider which one do you want. Now, that's one solution. Now, G2 CPU has come up, and we only announced it 2 days ago, with a new technology, a new standard, which we call test and measurement zip. Leverage the GPUs to compress the data before sending it to disk. What does that look like? And this is actually a demo that we can also show you on the showroom floor, should you be interested. We are reading from a VST, 5 gigabytes per second in a PXI chassis. And we are compressing it using the GPU. In this case, we're seeing a compression ratio, there we go, of 3.43, which means the data we're writing is at 1.46 gigabytes per second instead of 5 gigabytes per second. If we would use the SSD that's in this system, suddenly we're below that cache exhaustion speed. So we don't need to consider expensive RAID arrays. We don't need to consider expensive storage solutions. Now, of course, this is highly dependent on the type of data you have. Sometimes you have better compression ratios, sometimes you have worse. But it's a great way to, well, reduce the amount of data and, of course, the stress on your hard disk. I see I made a little typo in the PowerPoint. I do apologize for that. It shouldn't be overcoming cache exhaustion. It should be overcoming temperature or overheating. A lot of SSDs nowadays come with a heatsink. So it will look something like this. We can also bypass that, again, with RAID arrays. If all of the SSDs aren't working that hard, well, they're not overheating. And of course, test and measurement zip. If we're writing less data, then again, the SSD isn't stressed that much. Next up, controlling CPU execution. So some of you might have heard of some new technology where Intel is, for example, using a big little architecture. You have performance cores, you have efficiency cores. How do we leverage them? So the big little architecture, it's a basic principle. Sorry, lost my train of thought. So the big little architecture, it causes a couple of different problems. Systems with similar clock rates, with similar core counts can behave completely differently. One system can work beautifully and another system works barely at all. Important loops start competing with each other because maybe you are using a lower end CPU with more of these efficiency cores, which are slower, which means that suddenly your high priority loops that might need to be highly deterministic suddenly start fighting each other. And of course, well, a customer, they would prefer the cheaper option. And of course, there's a lot more context switching, which means jitter. I think I actually accidentally dropped the slides. So I'm quickly going to go into the big little architecture. So big lil, so you have these big, powerful performance cores. Often you will see them referenced as P cores. These are fast, often allow high performance computing. Beside that, you have the efficiency cores. Low power, they don't consume much power, they don't produce a lot of heat, but of course they're slower. And what you're going to see is, for example, laptops are going to have a lot more of these efficiency cores than a high-performance desktop solution, which has a lot more of these performance cores. So the same spec can give you completely different results. So how do we control that? How can we say, hey, this code needs to run on this specific CPU core? Well, LabVIEW, again, already has a solution for that, the timed loops. With the timed loops, we can decide on which CPU core we can actually run. So if we look here, if it's -2, we just tell Windows, okay, use whatever. But we can, of course, select which CPU core. But how would you know which CPU core is the performance and which CPU core is the efficiency core, right? Fast, slow. Well, let's consider this little benchmark. So what we're doing here, we're asking the amount of CPU cores that are available. We're generating some random data. And then we are just iterating through the CPU cores and just doing a couple of FFTs and seeing, okay, how fast does this go? And so when we run this, if we look at the task manager, you're going to see this peak traversing across all the cores. And it just keeps on going, so I'm quickly going to continue. And we're going to see something like this. On the left-hand side, the calculation time is a lot lower than on the right-hand side. It's a clear way to see which ones are the performance and efficiency cores. Now, is there a way to query this? At the current moment, no. But I have some rules of thumb that I use when designing a system to leverage this most optimally. Depending on the priority of these highly deterministic loops that definitely shouldn't do context switching, I give the high priority ones a low processor ID, which are normally the powerful performance cores, while the higher processor IDs tend to be the efficiency cores. It's an easy way for your system to be somewhat intelligent to make sure that while you're not using that context switching, which can kill quite a lot of the your determinism in, for example, a real-time system. There's that slide. Okay, that should have been at the beginning. I do apologize. So we have the big P cores. Where would we use it? Well, calculation helper loops, device communication, things that need to run fast and need to keep up. For example, DAC in and out, getting data in or out of the system. You really don't want that to start stuttering because then suddenly your loops start messing up. Might be better that the UI starts stuttering before the control loops do. The little e-cores, I tend to use them for UI calculations. Put the graphs on there, or the pre-processing of the graphs. Because if the UI stutters, okay, it's inconvenient for the customer, but it's more important that the system can keep up. For actor and DQMH cores, I tend to recommend the efficiency cores as well, saying, well, these DQMH cores, these actor cores, they tend to just be message handlers, so they shouldn't be that fast, so let's put them on the efficiency cores. And of course, things like state machines, which are just supervisory, just put them there. So that's how we control the big little architecture. That's how we can leverage these modern systems. Next up, we have algorithm optimization. So you've optimized your data types. You've optimized your architecture to call certain things. But now let's start talking about algorithms. How can we make sure our algorithms are optimized for high throughput? Think back to the 1 terabyte per second. I can't just go, oh, let's just fill it into all these different functions and hope for the best. No, we need to take our time to make sure we have a scalable architecture. This brings me to the delicious thing I stole from security, the Swiss cheese model. The Swiss cheese model is something that's used in security where people say, well, no security measure is perfect. However, if we have a security measure that does 90% of the work, or is 90% effective, and the next one is also 90% effective, it cascades down until barely anything is left. Now, what does that mean for us? Well, we have a high-speed data stream coming in, and we have a cascade of algorithms running in tandem. For example, on the left-hand side, it can be an FPGA or really efficient CPU cores or CPU algorithms, and gradually we go to less and less data until only the relevant things we are interested in remain. Relevant data snippets. Simple, fast algorithms. The simpler, the better. And then once you get to the end, complex, slow algorithms. A great example of complex, slow algorithms is AI. If you are streaming data at 50 gigabytes per second into an AI just can't keep up. But if we first reduce the data to only the relevant parts, the AI has a much easier time to do its work. So let's have a look at a couple of algorithms. So first of all, use simple algorithms. I tend to recommend going to the O notation, either linear ON or better. And these scale well on FPGAs, GPUs, and CPUs. It's often great if you have an algorithm that scales, that you can easily change between these environments. LabVIEW is built to switch between FPGA, GPU, and CPU. Well, leverage that. And you can do a two-step, or you can use multiple steps to gradually reduce the data and make it more palatable for data storage, for AI, and so on. This is one of my favorites, one of the algorithms, window min max. This works extremely well on GPU, CPU, and FPGA, and it's an extremely simple algorithm. All we're doing is, as the data is coming in, of course this is a highly realistic data stream that you're seeing here, we're taking windows off of it. We're taking certain amounts of time, and we're saying, this is what we're going to work with. And what we're going to do is we're going to grab the minimum and the maximum of each of these windows. Something extremely efficient to implement on the GPU, CPU, and FPGA. We're going to subtract the values in there. And based on that, so if we have a feature here, so here we don't have a feature, so this delta is quite low, right? Here, the delta is quite big, so we know there's a feature here. And same, delta is quite big here, we know there's a feature there. Now we know, okay, within that window, there's something of interest. Remove all the other windows, and I'm just sending over that window. So if you have events that come in very randomly and very sparsely, this is a great way to already reduce the data in a highly efficient way and cheap. It's a single counter and a couple of memory spots on an FPGA. You couldn't make it cheaper. So it's highly efficient. So FPGA, GPU, and CPU. Now, what if we don't want to detect transient behavior? We want to check when is the state of our system changing? Suddenly, a rod that we have shifted, how do we detect that? Well, for that, I tend to gravitate towards the windowed average. Again, we're taking windows, right? Trying to get to windows that we can reuse and throw away others. And we're going to take the average in there. Again, really cheap to do on an FPGA. Just take the sum and bit shift it, and you have the average. And then what we're doing is taking the delta between these. If there's no delta, or the delta between the previous and the next window is really, really small, there's nothing happening there. If it's really big, it means there was a state change. And you can take an action on that. This scales really well, and this is, for example, one of the algorithms used in that high throughput application. And then, of course, these windows can be passed on to algorithms which are much more expensive, but they don't have to run on the entire data set. They only have to run on potentially interesting snapshots. Again, works well with all compute technologies. Others, IAR or band stop or band pause functions. IAR is an extremely scalable and high performance filter technology. I strongly recommend this. And it scales well on FPGA, GPU, and CPU. You could also do FIR, but it tends to be a lot more expensive when you implement it on the FPGA. Next up, this is one I stole from the electronics, the leaky integral. So I don't know who of you here knows op-amps, but normally what you do when you create an integrator with an op-amp, you make it leaky, because otherwise it just starts saturating by itself towards its limits. Well, the same thing you could do here. Let's say you're searching for a signal of a certain strength. With the window min-max, all you're going to do is say, hey, there was a certain event here, but you don't know how much power did it have, and maybe you want to filter based on the power. So what we can do is what we call a leaky integral. It's just taking the sum of the samples as you go forwards, but you're constantly subtracting it again, so it tries to go to zero once again. And what that would look like is, well, you have that small feature over there, or short feature. It doesn't really go that high. Your integral, it only has a few moments before it stops and starts going down again. If we go to the big feature, that has a lot of power. The integral can go for quite a while and then goes down. All we have to do then is just check, okay, what's the height of that, and just extract that feature. It's a bit more advanced, but again, these algorithms are really efficient. They're extremely easy to implement in LabVIEW, FPGA, G2 CPU, and the CPU. Just food for thought, but definitely something to consider when you are working with high performance applications. And it could mean the difference between being able to place it on a supercomputer or an SB-RIO. By the way, this is my favorite supercomputer, the Cray. The reason for that is it has built-in seating. So it's actually heated seating, because the seating it's underneath it's power supply. So that's peak design in my opinion. But yeah, it just means that these complex algorithms, all your algorithms, can either fit on a small computer or a supercomputer just by being intelligent about it. So some example algorithms, advanced state machines, FFTs, AI and machine learning, wavelet transforms, and so many more. Well, by just being intelligent about how we approach that, it makes all difference. And so this is why I propose Swiss cheese model whenever you're doing really, really high performance computing. Let's get into the last part, GPU execution modes. So at the keynote, there was a lot of talk about GPU computing, but what does that actually mean? Well, people like to say, well, GPUs are great for really big calculations, really big FFTs, matrix multiplications, and so on. That's not true. They can do all the calculations, but you need to approach it correctly. So first of all, we have what we call the sequential elementary approach. I also like to call it the naive approach. This is how we would normally program in LabVIEW. We have some data on the inputs, and if we want to process it, well, we're doing it row by row. In this case, we want to do a little FFT, so we upload it to the GPU, we do our FFT, we get the data back, and we do that for a certain amount of iterations. Okay, that's not that bad if it's one, but let's say if it's thousands, a million of them, and it's a really small FFT. Well, suddenly what you're going to notice is, well, this GPU, it can only do a couple of megabytes per second. I was advertised gigabytes per second, tens of gigabytes per second. What's happening here? Well, this is what's happening. The GPU is constantly getting these little packages, and it takes more time to control the GPU than actually to do the operations. This is why there's also an alternative. We call it massive parallel processing. It's also called vectorization or tensors. And what it just means is we can feed in, for example, a 2D array to do a 1D operation. And what the FFT, for example, will do is it will go through all the rows for you really efficiently at the full speed of the GPU. Now, I know I'm talking about this, but what does that look like? What does that performance difference look like? Well, it's extremely dramatic. This is done on a PXI system I have at home. So there's a couple of things here. So we have a couple of colors. We are comparing a single-threaded, multi-threaded CPU versus GPU performance with the elementary approach and the MPP approach. Well, I think by now, looking at this graph already, you know which is which. The MPP approach, it keeps on going. Multiple gigabytes per second without any issue. While the dark green one, if you go through it sequentially and you send it these really small packages, the GPU is bored. It's constantly waiting for more data. You have thousands of CUDA cores, but if you only give it 100 samples each time, you really can't stretch its legs. So in those cases, the performance of your analysis is going to be even worse than the CPU, and quite drastically. So if we look here the CPU can go up to a gigabyte per second on 128 point FFT, and at the same time, what is that? Like 1, 2 megabyte per second on the GPU. If we go the other direction with MPP, in this case, on this GPU, that would be about 4 or 5 gigabytes per second. Incredibly drastic performance difference. And even though we're doing these small operations, 128 point FFT, because we're giving it enough data to work on at the same time, it can go through it quite quickly. So in this case, if we look at the data here, single-threaded CPU performance, at minimum, it was 40 megabytes per second. Maximum, it went at a blistering 484 megabytes per second, which is really good, in my opinion. Multi-thread CPU performance, even better. Minimum still 40 megabytes per second, but maximum of almost a gigabyte per second. CPU is quite powerful if you know how to leverage it. If you go to the elementary approach, the minimum GPU performance, 1.1 megabyte per second, that's tragic. That's useless, with a maximum of 3.7. While the MPP approach, even at its worst, is as good as the naive approach at its best. And its best is 6.22 gigabytes per second. This is on a fairly entry-level GPU, by the way. It's a very low power one, but it's very, very, very useful. This functionality, it's available in all the features in G2CPU, so now we're getting into the shameless plug. The machine vision, signal processing, data compression, high-speed I/O, all of these functions support that. And it's absolutely needed to really leverage a high-speed processing in LabVIEW. All these functions are also supported in Windows, Linux, and LabVIEW real-time. And in regards to hardware, well, we support both NVIDIA, Intel, and AMD. So you don't actually need a heavy-duty NVIDIA laptop. You could run this on a C-RIO. A ton of C-RIOs actually have a little iGPU baked in on the CPU. You can leverage it, tripling the performance of your C-RIO. And this is the reason why G2CPU can boast that we can do the fastest processing on the market currently today, due to that MPP and asynchronous zero copy technology, getting that data highly efficiently from the FPGA, VST, disk to the GPU and back. We can sustain throughputs on the PXI up to 7 gigabytes per second per GPU. On PCIe Gen 4, up to 24 gigabytes per second per GPU. And Gen 5, we can go above 53 gigabytes per second per GPU. Suddenly, that 1 terabyte per second becomes a lot more attainable by just looking at those numbers. On average, we're seeing a performance increase between 150 to 500 times compared to a CPU. So definitely useful. And the entire idea behind G2CPU is, if you can think of it, you can program it. You don't need to come to me and ask, or to us and ask, hey, can you create these custom kernels? No. The entire API, all 450 functions are available to you. So any algorithm you can think of, you can implement it. If you're wondering what that looks like, because I talked about GPU computing, but I haven't really shown it, well, it's quite simple. It's easy to understand. The functions look exactly like you would use them in LabVIEW. You can extend it with third-party toolkits, PyTorch, OpenCV, MATLAB, and so on. At G2CPU, we have the philosophy that the current AI landscape is changing so quickly that if we would implement a model today in LabVIEW, tomorrow it's obsolete. So rather that LabVIEW tries to keep up with Python, we're going to say, let Python lead the charge, and we're just going to stay compatible with them. Let the AI teams who know Python use Python. Let the engineers who are great in LabVIEW use LabVIEW, and let them work together instead of trying to get the engineers to use Python or the data scientists to use LabVIEW. It really improves synergy within a team. Also, we have wire probes, quite unique. So you can actually probe on the GPU and actually see what your algorithm is doing. So if something's misbehaving, it's always fun. And also, all our licenses are perpetual. So you only purchase it once. And if you want to upgrade, you can talk, but we can talk. But if you have a system 10 years from now, you need to maintain it, you can do so with the same license you purchased. And there's a free community edition you can download today. All licenses are on the NI website. So this is in partnership with NI. The free community edition, it does require a license, but you can freely acquire it from the NI website. So just request community edition. You just need to fill in your email, and that's it. You're good to go. One caveat with community edition, it is made for the community. It has most of the functionality in there. But given it's made for the community, it also assumes that anything you build in it is also made for the community. So everything within the license agreement, anything you build with it also needs to be made publicly available with source code and so on. Just keep that in mind. It's available on VIPM. And if you want the latest pre-release, go to g2cpu.com, resources, and you can try data compression, inter-process communication, and so on. All the stuff you saw today, all the stuff we're showing downstairs, you can use that today by just going to that website to get our pre-release. So with that, I want to thank you. If you're interested in GPU computing, I talked a bit about it, go to G2CPU. If you're interested in LabVIEW consultancy, qblogs.com. If you want to reach out to me, Natan.Biesmans@g2cpu.com. And of course, please visit us at the Radix booth. It's right at the entrance on the showroom floor. I'd love to talk more about GPUs. I think by now you know that. So all that's left to say is thank you. Any questions? Yes, sorry. Questions?
I'll pass the mic, but I'm going to shamelessly grab the first question.
Go for it.
Back to your Swiss cheese slide, I just want to check my understanding. Would it be correct to say that the simplest should go on FPGA, middle should go on CPU, and the last should go on GPU? Would that be a reasonable takeaway from the Swiss cheese?
I tend to go the other way around. So the FPGA first, definitely. Then go GPU. The GPU can do multiple gigabytes per second. And only once that's done, send it to the CPU to maybe go the last mile. The CPU, it can't do that much processing compared to the GPU. So distribute it in that way and you're going to be happy. Excellent. Any other questions? No? Oh, one in the back.
I guess if you've been haven't really gotten into the GPU side with LabVIEW before, and you're trying to kind of look for places to get your feet wet and to get started, any guidance for teams that are just starting out for looking for those kind of prime opportunities? I mean, I'm sure other than throughput, maybe that's obviously will draw your attention there, but any types of algorithms or things that you find are just kind of uniquely suited for that to kind of draw your eye when you're thinking about where you should start trying to fold this in more frequently?
Well, that's a good question. And of course, I don't have a straight up answer for that because it's really, really dependent on the type of application you're creating. But often what we're seeing is anything signal processing related, it just lends itself extremely well to the GPU. So often it's actually more cost effective to just put a GPU in there and just down spec your CPU system to then do the signal processing on the GPU. Or just spec it normally and you have that flexibility to go forward, right? How often do you have an application, signal processing application, where, okay, it's working now, and then suddenly another feature request comes in and you have to try and fit it in, but you have to optimize it. And well, what you can also do is say, well, I can already see that this is going to be a high throughput application. I'm going to go on the GPU, even though the CPU will be able to handle it. And you leave that upward mobility to add more algorithms to it, to maybe when the customer comes in and asks, well, we currently have one channel. That's, by the way, how that project started. We have one channel. Now we want 10, 16, 40, 128, all the way up to 10,000. Well, if you can take that along from the beginning, you leave that mobility, and then suddenly you can surprise your customer with saying, well, we can do this in, you got time next week? Instead of going, well, this is going to be 6 months to a year, and let's hope for the best. It just means buy a bigger GPU and you're good to go, or even just use multiple GPUs and just distribute the processing power. Jeff, just a sec.
Going back, way back in your presentation, you had the diagram with the different strengths and weaknesses of each.
That's way back.
The Venn diagram, yeah, almost your first slide. So I understand if you're doing a deterministic application, low latency, the FPGA is optimal, right? Because it's got basically zero latency. But what was it that you said about the CPU and the GPU, and which one is better for that?
Could you repeat that? Are you searching for latency?
Latency specifically. So I didn't understand the difference between a GPU and a CPU on a latency point of view. So
the CPU is connected to everything. So when it's trying to communicate with something, the latency tends to be somewhat constant, right? So the FPGA is super great. It's on a hardware level. It responds immediately. The CPU is whenever the scheduler does it. However, if you want to send data to the GPU from, for example, a DAC device, it first needs to go into the FPGA or the ASIC, then it needs to move to the CPU, and then it needs to go to the GPU to then do the operations, then send it back. It needs to go through quite a course to get to where it needs to go. The CPU, well, it's immediately connected to it, so it has a lot less latency. Often CPU, single-digit microseconds is feasible. I wouldn't try that with a GPU. With a GPU, what we tend to see is latencies down to 100 microseconds to single-digit milliseconds.
Okay, thank you. That's helpful.
To go a little bit further in that with GPUs, if you go to these really low latencies, you're going to see a decrease in throughput. There's a certain inefficiency associated with that, so don't expect 50 gigabytes per second and 100 microsecond latency. That's unfortunately not possible. So, preservation of misery. Any other questions?
Do you have any more of those little quotes you want to share?
We need to first get rid of my jet lag because I feel like some of them might be inappropriate.
Over a beer.
Well, coincidentally.
ask, what, did you want to say anything about the booth or coming to see anything?
Sorry?
Did you want to say anything about the booth or saying?
Yeah, I can do that as well while we're here. Thank you. So for those of you interested, we partner with Radex Technologies. They create a ton of high throughput, high performance PXI peripherals. Among them are GPUs that you can place in PXI systems. Really relevant, highly powerful, and cheap. A lot cheaper than an FPGA. And of course, if you want to use them, by the time you have an FPGA compiled, or the duration it takes to compile an FPGA, you have created a GPU application. Plus, you don't get that, hey, your FPGA bit file is 0.1 nanosecond out of spec, which is absolutely painful. So if you're interested in GPU computing, please come down to the showroom floor at the entrance, Radex Technologies, and we'll love to talk about that as well. Thank you.